Hello, welcome back to Physics 211, Electricity and Magnetism. We have been looking in this course mostly at electricity at the beginning, and then we recently got into magnetism, and we saw that a moving electric charge will generate a magnetic field. Now we're going to look at what happens with a magnetic field and see if we can actually generate some sort of electric current or some sort of electric charge that will come from having a magnetic field. So to do that, we're going to first review what we saw when we had, when we saw last chapter, when we looked at the moving currents. So first we started with an experiment in 1819 with Hans Christian Ørsted, and he had a wire, and that wire was surrounded by compasses. So we see these compasses here, and all of the compasses we see are pointing in the northerly direction. They're all pointing north like they should. And then what happened was Ørsted put a current through this wire. So now the wire is not just a wire, but it's a current carrying wire. And once there was a current going through the wire, all the compasses all of a sudden lined up and started pointing in the same direction in a circle around our wire. And we saw that we could take our right hands and put our thumbs in the direction of that current, and then our fingers will then curl in the direction of the magnetic field. Now, a lot of scientists at the time were very interested to see if a similar effect could happen with magnets. Could you have a magnet that would then generate an electric current? And so the person who was able to figure this out was Faraday. So that's why Faraday gets the credit. We call it Faraday's law. So here is a simulation showing us Faraday's law. So Faraday had this coil of wires here. And that coil of wires was hooked up to a light bulb. Well, we have it hooked up to a light bulb here, so that we could see if there is a current going through these coils of wire. And then we also have each end of our light bulb hooked up to this voltmeter, so that we can see what the voltage difference is across our coil of wires. Now, here's our magnet, and our magnet's just sitting there. And when our magnet's sitting there, we don't see any sort of light. There's no light going on in the light bulb. I can put the magnet right here. And if it's just sitting there right next to my coil of wires, nothing happens. However, I notice that if I bring the magnet into the coil of wires, right at the moment when it goes in, we see the light go up. Now, if I leave the magnet there, I leave it right in the center of the coil of wires, nothing happens. There's no current. So the magnet's inside the coil of wires, but there's no current. The light bulb's not lighting up, and there's no voltage change. Now, if I take the magnet back out, I see it lights up again. So let's try that again. When we put the magnet in, we saw that the voltage moved to the left, to the negative side. And we saw that the light lit up, but nothing happened when it just sat in the center. Now we take it back out, and now it moves in the opposite direction. So now we have a voltage change in the opposite direction when we take it back out. Now we can also take our magnet, if we leave it right there in the center, if we change its polarity all of a sudden while it's sitting there in the center of our coil of wires, we see that we do get a big change in the voltage, and we saw that the light bulb lit up. We can turn on the field lines here in the simulation as well that give us an idea of what's going on with the magnetic field, and we can think about how that might affect things. We can also look at two different coils, and we can see what the effect of different coils would be on our having that for our magnet as well. So I want you to play with this simulation. There's a link to it here. So I want you to play with it and see what you can discover about moving your magnet into different coils of wires and how you can get different reactions. All right. Now, what we noticed when with Faraday's law that we just saw is that when a bar magnet is pushed into a coil of wire, it causes a momentary deflection of the current meter needle. And in this case, we also saw with the simulation we were using that we saw a change in the voltmeter. And holding the magnet inside the coils, just letting it sit there right inside the coils, we saw that there was nothing going on, right? The light did not light up, nothing happened when the magnet was just sitting there right in the center of the coils. So there was no effect in that case. And a quick withdrawal of the magnet deflects the needle in the other direction. So we saw that when we put it in, the needle went in one direction, we took it out, the needle went in the other direction. Now, some of Faraday's other experiments, he wanted to see what happened. So here's the example from Faraday's experiment that we just were looking at. If we push or pull our magnet, we see that we were able to get our current meter, and what we were looking at was actually a voltmeter, and see that that deflects either side. And our current meter was basically our light bulb. Now, this is another experiment that Faraday had. In this case, he has two coils of wire, one on top of the other. And he expected that when he had a current going through one of those, since we know that would generate a magnetic field, that would then hopefully generate a current in the coil of wires below. So he would turn it on, close the switch, and there was no current after he closed the switch in the coil of wires below. But then he started to notice that when he opened and closed the switch, right at that moment, there was a jump in the current. So when one coil is placed directly above the other, there is no current in the lower current while the switch is in the closed position. So when there's current in this upper current, and there's actually current there, we know that we can take our right hands and we can figure out that if there's current, then there is a magnetic field. Even then, there was no current in the lower coil of wires. But a momentary current appears whenever the switch is opened or closed. So just opening and closing it, right at that moment, we do get a current. Now, Faraday also wanted to see if he took a coil and put it inside a magnetic field, so a giant, just permanent magnet, and pushed or pulled the coil inside the giant magnet, what that would do. So a momentary current is produced by rapidly pulling a coil of wire out of a magnetic field. So right at the moment when it is being pulled quickly out of that magnetic field, we do see a current. Pushing the coil into the magnet also causes the needle to deflect, and this time in the opposite direction. So now that we've been looking at these experiments, let's see if we can understand what is going on. So if we have a conductor, so this is a conductor right here with this conductor, and we take a conductor and we move it through a magnetic field. So here's our magnetic field. We see that there are X's that indicates that the magnetic field is into the page. So the conductor is moving with a velocity here indicated to the right. And in this case, we know that if we take our right hands, we can take our right hands and we can say, well, if the velocity is moving to the right and the magnetic field is into the page, then the force is up. So that would look like this to you. Then the magnetic force is up. And so in that case, we can say that positive charges are moving up, or we can also say, as we normally would, that a negative charge is in fact moving in the opposite direction. So we're going to end up with negative charges on one side and positive charges on the other. So here we have our positive charges. We've had a charge separation where we have positive charges on one end and negative charges on the other, just by moving our conductor through a perpendicular magnetic field in this case, or just through a magnetic field. And we see that in this case, we end up with the positive charges on the top and the negative charges on the bottom. And we know that this was due to the fact that we had this force, this magnetic force that was moving the charges to the top and the other charges to the bottom. Well, the negative charges to the bottom. And in that case, what we have is a charge separation. So we now have an electric field that will point from the positive charges to the negative charges. And so now we'll see that we also have an equal but opposite electric force due to the electric field pointing downward. And so these forces, the magnetic force and the electric force, are equal and opposite. So we can set them as equal to each other. And we know that the magnitude of our magnetic force is QV cross B. So we can write that as QVB. And the magnitude of our electric force is Q times E. So I can go through and set those equal to each other. And since I know they're equal, I can cancel out Q because that's the same charge for both of them. And I see that the that VB equals E, which tells us, in fact, that the electric field in this case is equal to V times B, the magnitude of our electric field. So we write this out and we say that in that case, the magnetic force on the charge carriers in a moving conductor creates an electric field of strength E equals VB inside the conductor. So that's due to the fact that the magnetic forces separate the charges and cause a potential difference between the ends. So this potential difference that is caused is the motional EMF. So let's think about what that potential difference would be. Well, we know that the electric field is equal to V times B. And we know that the potential difference is equal to negative the integral of E dot ds, where in this case, I can say that that is the integral for E dot ds is going to be along this length, L. From 0 to L, we can integrate 0 to L. And in that case, our electric field is going the opposite direction. So that would be a negative E times dl. And so doing that integral, I end up with the negative of a negative. And so I end up with E times L. So delta V equals E times L. And rewriting that, I know that E is VB. So delta V equals VB times L, which I can have rewritten right here as delta V equals VLB. So for a conductor of length L, the motional EMF, so this is the motional EMF. We're going to call that an EMF. So this is now an EMF. So the motional EMF perpendicular to the magnetic field is VLB. Now let's look at an example using this. So here's an example. We're going to be measuring the Earth's magnetic field. So the magnetic field over northern Canada points straight down. So that's good. It's easy to measure if it's going straight down, nice and perpendicular. The crew of B-52 aircraft flying at 300 meters per second over northern Canada finds a 0.95 volt potential difference between the wingtips. Now the wingspan of a B-52 is 56 meters. So what is the magnetic field strength there? Well, first let's draw our picture. There's our B-52. And we know that it is flying with a velocity moving forward. V equals 300 meters per second. And that the magnetic field points straight down. So if we're looking down on our B-52, we see that we have a magnetic field pointing straight down. And we measure the wingtip here, from wingtip to wingtip. That length is, this is the length L here, L. We know that L equals 56 meters. And we found that the potential difference between the two wingtips from this point to this point, delta V equals 0.95 volts. So if we write that, so we remember that the EMF, the induced EMF, is going to be equal to VLB. So we can rewrite this as we want to find the magnetic field. So what we're interested in finding is the magnetic field strength. So we rewrite this as B equals the EMF over VL. And so B, in this case, will equal our EMF, which we found to be 0.95 volts, over the V, the velocity that's going, of 300 meters per second, times the length of the wings, which is 56 meters. And we find that in this case, B is equal to 5.7 times 10 to the times 10 to the minus fifth. Teslas. And we know that that seems reasonable because the magnetic field on the Earth is about 5 times 10 to the minus fifth Teslas, and we are up closer to the northern pole, so we would expect it to be a little bit higher. So if we're looking at the fact that we have this induced motional EMFs, this is our motional EMF. This is the motional EMF. Well, if we have we can also get an induced current. And we see that the charge carriers in the wire, as we're moving a wire, here we have our wire moving through a perpendicular magnetic field where the magnetic field is going into the page. And this is a conducting rail. So the whole rail here is conducting. So this wire that's going across, that is actually closing our circuit. And this is movable. So this piece right here moves. Well, the rest of the wire is stuck in place. It's fixed to the table and doesn't move. So as we, so we have the positive end of our wire here and our negative end of our wire here. So as we move our wire with a velocity v into our field, we know, of course, we can take our right hands and we see that the force will get us to have our positive charges on this side and our negative charges on the other side. And so the charge carriers will then flow around the conducting loop as an induced current. So now that we have a full loop, we can actually get a current, not just a charge separation, not just a motional EMF, but we can actually get a current. And so here's the current that we end up getting around our loop. So if we slide a conducting wire along a U-shaped conducting rail, we can complete a circuit. And now, because we have that motional EMF that we just saw, that we were able to get that separation of the charges to give us this potential difference between either side of the conductor, now we can generate an electric current. So if the total resistance is R, the induced current that we're now generating will be given by Ohm's law, which remember, Ver. So Ohm's law is Ver, delta V equals IR, which we can rewrite if we want to get the current as I equals delta V over R. And that delta V we said is that EMF. So we're going to rewrite that as I equals EMF over R. And remember that we found that that motional EMF is equal to VLB. So taking this and putting this in for our EMF, we see that I equals EMF over R, which is VLB over R. So our induced current will be equal to VLB over R. So now we know that we have this induced current, and we have to somehow keep that wire moving. So the induced current is flowing through the moving wire, and there is a magnetic force, as we know from the fact that we did our V cross B, QV cross B gives us our magnetic force. And that is in the opposite of that's going to be opposite the direction of motion. It's always the opposite of the direction of motion because it's QV cross B. And so we have this magnetic force on the current carrying wire that's opposite the motion. And so in order to have that work, to keep the wire moving at a constant speed, we must apply a pulling force. Otherwise, we will be retarded. That retarding force will slow down our wire and we won't keep moving. So we have to have a pulling force that'll be equal to F pole equals ILB. And we remember that that I right there, that I, and this is due to the magnetic force on the wire. That's ILB from before we saw that. And so that I, of course, is equal to VLB over R. So taking this VLB over R and putting it in here for our I, we see that the pulling force is equal to VL squared B squared over R. Now, to think about this in the best way, we don't want to just think about the force that's being done, but we actually want to think about the power. And the power is the rate that the work that is the work that it's done at a certain rate. So this pulling force does work at a rate that's equal to the power, which is equal to F times V. So now we're just going to multiply this F right here that we got times V. So we end up with V squared L squared B squared over R. And all of this power is dissipated by the resistance of the circuit. And we remember that that dissipation of power in a circuit is equal to I squared R. So if we take I right here, we can say that that is equal to I squared. So I'm going to say V squared, L squared, B squared over R squared times R. And so those R's cancel. And I get V squared, L squared, B squared over R, which is exactly the same as the power going in. So we see that the power that is put in is coming out. So it's totally equal and is completely dissipated by the circuit. So now this figure shows a connecting wire that is now sliding to the left. So now if we're sliding it to the left, we now need to keep pushing it to the left because now our retarding force due to the magnetic field is to the right. So in this case, a pushing force is needed to keep the wire moving at constant speed in the opposite direction. Again, if we did that same calculation, we would see that this input power will be dissipated entirely by the electric circuit. Now, one application of something like this way that we can generate this electricity by moving a conductor in a magnetic field is called a generator. So we're going to look at that as well. A device that converts mechanical energy to electric energy is called a generator. So we've seen that we can actually generate electrical current by just simply moving a conductor in a magnetic field. And we'll look at some more of this in detail later.